All right, so here's the objective today. We're going to try to go through. Hey, shh. We're going to try to go through 8. Is it 6 or 8 of these? 8 of them. Okay, there's 6 types, but 8 problems. The first objective we're going to do is we're going to identify these types of reactions, and then the second thing we're going to do is we're going to learn how to balance these reactions. Now, again, I assure you, this is going to go much easier than the last time you probably did this in terms of balancing. It becomes second nature, and it becomes very simple and very easy. I have 2 ways to teach it. I have a mental way to do it, and most people grab the mental way immediately. And then I have a mathematical or a methodical approach. And so you just kind of have to, if you get to the point where you can't do it mentally, I will show you the math part. But I don't want to do the hard part if everyone can do the easy way. So that's the objective we want to do. So, types of reactions. So remember, there are 6 basic types. Now, on that worksheet that you guys saw the other day, you only saw 4 of them. You saw what is the name of the reaction when 2 or more simple or complex compounds react to form one single compound? Synthesis. Very good. Okay. Yes, synthesis must result into one more complex compound. Okay. What happens when you take one complex compound and you break it into multiple parts? Decomposition. And I'm just going to write decomp for short. All right, what happens when you have a compound that reacts with a single element and one of those single elements swap places with one of the things in the compound? Single replacement. Well, that's difficult. You will always see me probably write it as SR. Okay. The next type is when you have 2 compounds and those 2 compounds react and they swap places. What type is that? DR, double replacement. All right, so the 2 that we need to add today. Actually, let me grab my folder. You okay over there? Yeah, I am. Okay. There are 2 more. Actually 3 more, but we're not going to get into the 7th one. All right, the next one is, I want you to write this word, and then underneath it write this word. Combustion. Okay? Now, to be honest with you, yes, one of them is combustion, and we will see the combustion one today. And then the next one. Now, I know where I wrote it is kind of weird, but I wrote it right there on purpose. Because double replacement reactions are a general type. But there is a special type of double replacement that you can identify, and it is known as an acid-base reaction. Okay? And we'll talk about how you can identify it as an acid-base at a later date. But today, as a matter of fact, I think one of these problems is an acid-base reaction. Yes, one of them is an acid-base. So let's jump in here and let's see if we can identify the types of reactions. So first one, let's look at what's going on in number 1. So we've got LiH. Is this a compound or is that an element? It's a compound, okay? And plus F2. What is that? It's an element, okay? So you've got a compound plus an element, and then all of a sudden, again, remember, what does this thing mean? A reaction has occurred. All right? And what happened after that reaction occurred? Okay. So essentially, if you think about it, would you agree that the F came over to this compound and kicked the H out? Yes. Okay. So what type of reaction would this then be? This is a single replacement. Okay. This is a single replacement reaction. Now, remember I brought up 3 people? I brought up Mackenzie, Lucas, and Sam. And I said, all right, Mackenzie, you have the option. But I told you there was something special that in chemistry you have to look at to determine if this is even possible. So remember what that thing is called? For these types, you need something called the, need the activity series. So essentially, the fluorine has to be more active than the hydrogen to kick it out. Remember, so basically that would be like if Sam and Mackenzie were at the dance together and Lucas walked in, what happened? What happened? You want to say that again, Sam? So essentially, Sam got kicked out and was replaced with Lucas. But that's what's going on in these single replacement reactions. But again, you would have to look at the activity series to see which one is more active than the other. Let me just kind of throw this out there, just kind of fishing for something. Is there any way anyone can tell me, based on this reaction, that you would know fluorine is more reactive than hydrogen? Yeah, that is true. You can see that because fluorine is replacing hydrogen, then it is more active. But I'm looking at, even if you didn't see the final results, could you still know fluorine was more reactive? It's the most electronegative. And what do we know about fluorine? Its electronegativity. It's the highest. It is going to take electrons. And so this is why it has that ability to jump in that compound. Okay? In a weird, strange, not yes, but not no. There's a list, and I'm going to give you the list, and it'll just be understandable why it's that way. Okay? And it has to do with fulfilling the valence shell, so it kind of has something to do with electronegativity, but kind of not. It's weird. All right, number 2. You've got this thing. Now, let me ask you, what is that thing, a compound or an element? It's a compound. And what happened to that compound? It broke apart. So this is simply what type? Decomposition. Okay, very easy decomposition. Okay, all right, let's look at the next one. Number 3. Okay, all right, so let's look at this. We've got a compound plus a compound makes a compound and another compound. But are all 4 compounds the same or different? They're different. So if you notice, and this was kind of weird, simply because, and you'll know why in a minute, but this is the thing that's going to throw everything off. But can anybody guess and tell me what type of reaction this would be? This is a double. And the way I want you to look at it is on the reactant side. Now remember, what side of this arrow are the reactants on? The left side. I want you to look at the sulfate and who it's with on the left. And I want you to look at the gallium with who it's with on the left. Do you agree that they're in separate compounds on the reactant side? And then what do you notice about them on the product side? Do you agree that they come together over there? So what happens is that basically Ga swaps with H. Would you agree with that? Okay, so that's kind of what's going on. So this is what type of reaction? If you wrote double replacement, hope you have enough room to correct it. And here's why. On this other slide, I told you that there was a special type of double replacement reaction, and it's called a what? Acid-base. Okay. So here's a little bit of new knowledge that you guys have to understand what an acid is. An acid Okay? That's something that's very important. Something that's very important. Very good. It's exactly how you measure pH. Now, if you know what an acid is, that's all well and good. But the problem is, my first question is, what is a hydrogen ion? It's just an H, right? Okay. But here's the part that some students don't remember. What is a cation? No. It is positive, but when does a cation come in a formula? The beginning. So the formula that is written is H2SO4. Would you agree or disagree? Agree. Now, do you agree that an H is written first? Okay, so this started technically as H+. Would you agree with that? But let me ask you something. Where in the world did that 2 come from? Came from sulfate. So this thing is the what? So we've got the cation, and what is this thing? This is the anion. Okay, and the anion was sulfate. Now, if you write them like that, if you crisscross the charges, does that give you the formula above it? Yes. Let me ask you, does anyone know the name of this acid by chance? Nope, it's just sulfuric. This is sulfuric acid. Yep. Have you learned that from me, or did you know that before me? Have you learned that from me? Okay, well done. Well done. Okay. Now, the other compound listed is it GaOH3? Yes, no? Okay, GaOH3. Now, let me go back and look. Actually, wrong button. Let me go back here. You got to understand what a base is. Okay? And a base has a hydroxide as an anion. Now, I'm going to go ahead and tell you real quickly, that statement is a bold-faced lie. Okay? However, for your need-to-know knowledge in this course, it's accurate. Okay? And here's why I need you to understand that. All bases do not require the hydroxide. But for your knowledge in here, they do. There's only one base that I may throw at you that does not require the hydroxide. And we'll get to it a little bit later on. I promise you it'll make a whole lot more sense next year. Don't worry about it. All right. So, going back to this, we now know, and I'm going to kind of erase all this, we now know that we have this hydrogen ion, which makes this thing an acid, and we have this thing that's hydroxide as the cation, which makes that thing a what? A base. So, now, what type of reaction is this? This is an acid base. Now, let me ask you something. This is an important question. Are all double replacement reactions acid bases? No. But listen to the follow-up. Are all acid-base reactions double replacement? Yes. Okay. Now, there's one other piece of knowledge that I want to instill in you. And this is important. All acid-base reactions have the same 2 products. The first one is always water. The second one, and this is the one that always blows everyone's mind, is a salt. A salt. Okay. Now, exactly. Because anytime that teenagers or younger or lack of experience in chemistry hear the word salt, what comes to mind? Sodium chloride. It's been a lie your entire life. Okay? And the deal is that you have been told that the only salt is sodium chloride, sodium iodide, something like that. That is the farthest thing from the truth. The farthest thing from the truth. So you guys have got to get it through your heads, which is a difficult task, that the only salt on the planet does not go on French fries. Okay? Depends. Now, it depends upon the type of salt. I'm fixing to throw you for a whirl. There are 3 different types of salts. You just went there, didn't you? There's a basic salt, there's a neutral salt, and there's an acidic salt. Okay. No. No, when you say salty, what is salty? I mean, I'm serious. Hang on. Let me show you what I'm talking about. All right, I want you to write this down on the back. If I asked you what is the most famous acid that would come to mind, what would you say? Hydrochloric. It's always the acid I always hear. This is the chemical formula for hydrochloric acid. Okay. Stop, Dustin. Stop. Hydrochloric acid. We cool with that? Now, a base that you would need to become familiar with is this one. Now, if I asked you to name that thing, what's the name of that thing? This is sodium hydroxide, okay? So, this is your acid, and this is your base. Now, I just said a few minutes ago that all acid-base reactions always have 2 products, water and a salt. Now, let me ask you, I just asked you this a minute ago, are all double replacement reactions acid-base? No, but are all acid-base double replacements? Yes. So let me ask you something. If Na, it was with hydroxide on the reactant side, and chlorine is with hydrogen on the reactant side, what happens on the product side? Okay. So, remember you told me that it produces a salt and a water. Now, if you do it like a basic, very basic, simple double replacement reaction, you're going to get NaCl plus HOH. And that last thing looks kind of funny to you. Okay? Now, the reason it looks kind of funny to you, because if I said write the chemical formula for water, you would not write HOH. What would you write? You'd write H2O. But is that the exact same thing? Yeah, you just separated the hydrogens. Okay? Which is exactly the same thing. But if you think about it, remember, would you agree that this right here is the cation? And that right there is the anion. Here's the most important thing about chemical reactions. On the other side, can a cation and a cation be together? Why not? What's the charge of a cation? Positives. What do 2 positive things to do? They repel each other. So that's why it has to be a cation and an anion that react. So if I took hydrochloric acid and I poured sodium hydroxide in it, I would get a salt water solution. But here's the problem. When I say the word salt, is it always this stuff? No. It could be anything. Now here's the deal. Do you agree that you would have it would be like salt water floating around in the solution? How could I, this is experimentally, how could I get solid sodium chloride out of that beaker? Boil it. When you boil it, what's going to happen? The water leaves. Well, what happens when the water leaves? The solid salt is left behind. Yes, sir. Yes. Okay. Solvent. Salt. It is the cation of the base and the anion of the acid that come together.
But like that's the definition of just any salt.
Yes, sir. Depends on which type they use. It's probably sodium iodide.
Will different types of salt give me a heart attack faster than others?
I don't know. All right, so let's move on. All right, number 4.
I mean, I'd recommend just sticking with the sodium.
Number 4. You've got a single element of nickel reacting with lead 2 nitrate, and then it reacts, and now all of a sudden nickel is now with a nitrate, and who's by itself? Lead. So what type of reaction would that be? Single replacement. Very good. Now I'm going to skip number 5. I don't want to come back to it. There's a reason why I want to come back to it. Okay. All right. So let's go to number 6. So you've got sodium sulfate and zinc bromide on one side, and then what happens on the other side? Who is sodium with on the other side now? Bromine. Well, who was bromine with originally? Zinc. Okay, so what happened? Right now? Who? Zaba and Emily. Mr. Pinson needs to see y'all. Emily's not here. No. So what type of reaction would this one be? Think about it. Do you agree that sodium swap places with zinc? So how many things moved? 2 things moved, because the sulfate also moved, because you have a compound plus a compound made a new compound and a new compound. So this is double replacement. Now, remember what we said earlier. Are all double replacement reactions acid-base? Is this an acid-base? You have no acid and you have no base. So this is a straight double replacement. Now, number 7 is kind of funky. And it has 3 things reacting to form one thing. So what type is this? This is synthesis. Very good. This is synthesis. And then finally, number 8, you've got a compound plus a single element that react to make a brand new compound plus a single element. So what type would this be? This is a single replacement. You kind of starting to figure out the differences now? All right, so let's go back up and let's look at number 5. And number 5 is going to be a new type that you've never, ever, ever heard of. And I'm going to just go ahead and tell you what the answer is and explain it. This is combustion. Okay, this is combustion. Now, I'm going to come off of this page to be able to explain this, and you may want to write this down on the back. C3H8 is it, right? C4H what? No, actually, this would be, by name, this is methene. Methane. Yes. All right, so under this word right here, I want you to write this word. Write that blue word under that formula. What is that word? How do you know that that formula is a hydrocarbon? Wow. There's a hydrogen and a carbon. Dang. Sarah, that's tough. Okay. Now, hydrocarbon, what is O2? Now, let me ask you something. Why is this mysterious little 2 right here? Thank you. Say that word again. It's a diatomic. How many diatomics are there? They all end in gen. Hydrogen, nitrogen, oxygen, and the halogens. They all end in gen. Now, here's the cool thing about combustion reactions. These 2 things are always the products. Those 2 things are always the products for combustion reactions. Now, remember a minute ago when I told you that I'm kind of lying to you? I'm lying to you just a little bit again. However, for your need to know knowledge in this room this year, that is always true. Bingo. So, but let me ask you something. If I were to take you to the gas station and give you a match and say, light it and run.
That made me a terrorist. You wouldn't be able to run.
The first question is, if I put the gas station in a vacuum, now I'm not talking about a Hoover that vacuums your floor. What I mean by a vacuum is a room that has 0 air molecules in it. First of all, could you even light the match? What has to be present for something to burn? If you do not have this stuff right here, nothing will burn. Nothing will burn. So if you light something in a bottle and it reacts, blah, 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 something blows up, can you come back immediately and redo it again? No. What have you done with that initial burn? You've burned all the oxygen out of it. What?
Like if you set a fire in a space station, you have to put it out for years, it burns all the oxygen from the sun.
Yes, exactly. Okay. Now, so there are 3 ways you can determine if a reaction is a combustion reaction or not. What's the big fancy strange looking thing in the beginning? A hydrocarbon. And again, how do you know that this is a hydrocarbon? There's a hydrogen and a carbon. Now, will the 4 and the 8 stay the same? No, they'll always be a little bit different. But it must be reacting with what thing? Oxygen. And what will the products always be? CO2 and water. Okay? So if you recognize 3 of the 4, then you'll always know that it's a combustion type reaction. Okay? So that's what's going on there. So that gave us the types of reactions. Now let's go back, and I know we're getting a little limited on time, but I want to do as many of these as I can possibly do. So I want to go in, I want to try to balance these things, and here's what I want you to understand. Why do we balance things? What's the purpose of balancing? Actually, that's the perfect answer. There's something called the law of conservation of mass, which means what you start with, you must end with. And you have to have the same number of atoms on both sides. So let's start with what we know. And again, I know it's been a while, but I'm going to do this mentally and see if we can fix it. On the left, and again, the arrow is the hinge point. Okay? On the left side of this reaction, how many lithiums do you see? 1. How many lithiums do you see on the right side? So do I need to even worry about my lithiums? No. Okay? Now, hydrogens, how many do you have on the left? 1, but how many do you have over here? 2. That's a problem. Now, here's my issue. Can you come in and watch where I put this? Can I put a 2 right there? No. Never, ever, 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 ever add subscripts. Where do you put the numbers to balance an equation? In front. And what are those numbers called? Coefficients. So, if I've got 1 hydrogen on the left and I've got 2 hydrogens on the right, how would I balance it? Put a 2 in front of the entire compound. Now, you are all smart enough to know that a property in math now has to be dealt with. What is the property called when a number goes to everything that it's attached to? Distributed. So now, do I have 2 H's? But what just happened to my Li? Now I have 2 over there. So did that just throw off my number on the right-hand side? So here's the deal. I know my hydrogens are good. Well, I just screwed up my lithiums. So how can I correct the lithium? If I add 2 there. Hold on. Stop. Stop. Now, again, the same property applies. I've got 2 lithiums, and now how many fluorines do I have on the right-hand side? But is that a good thing? Why is that a good thing? Because how many do I have over here? 2. So before you ever finished, once you feel like, okay, I think I got it, go back and double check. On the left, how many lithiums? 2. On the right, how many lithiums? 2. On the left, how many H's? 2. On the right, how many H's? 2. On the left, how many F's? On the right, how many F's? You're good. It's problem is balanced. Now, this is something for me in my class, and I need you to understand how to do this. And it's how to properly report a balanced equations answer. And it's very simple. What you're going to do is you're going to pretend that each coefficient is a set of numbers. Now, technically, do you agree that there's a blank right here? But what's understood to be there? A 1. So let me show you how I want you to report this. 2, 1, 2, 1. Just kind of stare at it, see if that makes sense. So for every line, you have to have a value. Does that make sense? And if you don't have a value written down, what's understood to be in front of it? A 1. So does my system make sense? The only reason I do this is it makes it really easy for me to grade it really fast. So if I'm just looking down your sheet of paper, I'm looking for a set of numbers. Okay? All right, looking at the next one. Number 2. Let's start with what we know. Here's the only part that I need to ask and make sure of. This 2 sitting way back here, does it apply to the iron out front? It does not. Why does the 2 not apply to the iron out front? Because you distribute to things only where according to the parentheses inside of it. Does that make sense? All right. So how many irons do I have on the left-hand side? 1. How many irons do I have on the right-hand side? 2. Is that a problem? Yes. So what do? Put a 2 right here. And let me ask you something. This is where your brain now has matured enough that you can understand this concept. Now, do you agree that this 2 is distributing to the H and the O? But what is this 2 out front also doing? It's distributing to it as well. So let's start with the H's. How many H's do you now have on the reactant side? 4. How many do you have on the product side? 2. How do you make those things equal? If I put a 2 right here, what does that give me? Gives me 4, right? It's normal. Don't care. Last problem. How many oxygens do I have on the left? I've got 2 plus 2 is 4. And this is where every year students kind of get bogged down in this. Do you agree that an oxygen is here and an oxygen is here? What mathematical equation sign is between those two formulas? An addition sign. So how many oxygens do I have there? You know, let me step back for just a second. I know exactly what happened. Hold on. Completely ignore me for just a second. We'll come back to that one tomorrow. Completely ignore it. Completely.